So today we're going to talk more specifically about collisions and about those two different types of collisions we talked about. The first of which was elastic collisions. Remember, elastic collisions are ones in which they come in contact and then they bounce off of each other, so they don't stick together. They come and they rebound from each other. Inelastic collisions are the opposite of that. They will collide and then stick together and continue as one single object. Okay, so they start as two separate objects. They come together to collide as one singular object. So you need to know the difference between those two types of collisions because the equations used are different for each type. Okay? But in any sort of collision, the momentum is conserved. And we mentioned this on the very first day that momentum is conserved in each of these. And when we say conserved, we mean that it is not gained or lost, right? No momentum is gained or lost in this collision. Okay, so while these two objects are colliding, no momentum is gained or lost. There is kinetic energy that's gained or lost, but there is no change or no transfer, no loss of momentum. Okay, there is a transfer. It doesn't matter the mass, velocity of either object. There's always a conservation of momentum. So what that means is that the momentum before is equal to the momentum after, and that's of each individual object. Okay? So I'm going to show you the equation first here for elastic collisions. Okay, so the equation I'm about to put up is for elastic collisions. Okay, and you need to understand the difference between those. This equation should go on your equation sheet. This is one that we will use a lot for this chapter. Okay, so this is an equation here for the conservation of momentum in an elastic collision. Okay, elastic. So if you look at each of these individual terms, you can see that mass times velocity of the first object plus mass times velocity of the second object, which is essentially momentum of the first object plus momentum of the second object, equals mass times velocity of the first object, and then it's got this little sign up here that we call prime. Okay, so m1 times v1 prime, and what this means is after. So when we see that little apostrophe, that means prime, and that means after the collision. Okay, so essentially what we're seeing here is that the momentum after the collision of the first object plus the second object is equal to the momentum of the first object plus the second object before the collision. Okay, so whenever we see this apostrophe up here, that we call it prime, right? So if I'm talking about v1 prime, that means I'm talking about the velocity of our second object after the collision. Okay, so if I say v1 prime, that's what I'm looking for. I'm looking at the momentum, at the velocity of our first object after the collision. Okay, mass times velocity plus mass times velocity equals mass times velocity prime, mass times velocity prime. So we're going to go ahead and try a practice problem here with our elastic collisions. So the equation that I just gave you is the one that you're going to be using here. So if you need to go ahead and pause the video to get this written down, go ahead and do that. But I'm going to put the equation up here. Okay, so let's go ahead and work through what our problem gives us. First of all, it tells us that the mass, let's just talk about the problem itself. Find the recoil velocity of a 5 kilogram rifle that shoots a .05 kilogram bullet at a speed of 120 meters per second. So let's visualize what's happening here in the motion. As you fire a gun, the bullet leaves in the forward direction, and the recoil velocity is essentially the kickback of that gun. Okay, it's going to come back and hit you in the shoulder as you fire that gun. So that's what we're trying to find, is with what speed is the rifle recoiling or kicking back at you because it's heading in the backwards direction. Okay, so they're going to leave in opposite directions, or they're going to move in opposite directions after that collision. So here we're assuming that everything starts at rest, and we're assuming that as soon as the bullet is fired, as soon as the gun is fired, that's considered our collision. Okay, that's where the change happens. So that's considered our collision here. These two things aren't necessarily coming to collide with each other, but they're starting at rest. As soon as that gun is fired, that's considered our collision. Okay, so let's work from there. We'll consider the gun here to be our rifle, our first object. So that means M sub 1 is equal to 5 kilograms. V sub 1 initially is at rest, right? Both the bullet and the gun start at rest. Okay, and since it's not V1 prime, we're talking about before the collision. Okay, mass of the second object is mass of the bullet, and that tells us it's 0.05. And we also know that it starts at rest, so V sub 2 is equal to 0. Okay, there's one other thing that we do know, and that's that the bullet leaves the gun at a speed of 120 meters per second. So that means V sub 2 prime is equal to 120 meters per second. Okay, and we consider that to be the positive direction, whatever direction the bullet's leaving at. So that means the recoil velocity or the kickback velocity that we're going to try to solve for should be negative, right? They're going to come back in opposite directions. But we'll see what the math tells us here, okay? So let's go ahead and start plugging these into our equation. We're going to solve for recoil velocity, which means we're solving for V sub 2 prime. I'm sorry, V sub 1 prime. We know V sub 2 prime. All right, our question is to solve for V sub 1 prime. Velocity of the bullet. I'm sorry, velocity of the gun. I can't talk today. All right, so let's go ahead and plug these into our equation. M1 times V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. All right, mass of the first is 5 times 0. Mass of the second is 0.05 times 0. Mass of the first object is 5. We're solving for V sub 1 prime. Mass of the second object is 0.05 times 120. Okay, so our whole left side of our system is a 0, right? It starts with initially no momentum. So now to get this V1 prime by itself, I need to subtract the 6 to the other side, which gives me negative 6 equals 5 V sub 1 prime. And I know that's covered up a little bit here. I'll move it over. Negative 6 equals 5 V sub 1 prime. I'll divide negative 6 by 5 and get V sub 1 prime to equal negative 1.2 meters per second. Okay, so what that's telling us is that the rifle or the gun is going to head backwards, head in our direction, right, opposite the direction of the bullet at a speed of 1.2 meters per second. All right, let's go ahead and try another one here. So pause your video and get this written down. This tells us two pool balls of equal mass collide. First is moving at a speed of 3.1 meters per second. The second was at rest. If the collision was perfectly elastic, what is the speed of both objects after the collision? Okay, what's the speed of both objects after the collision? So here, essentially, it tells us that M sub 1 equals M sub 2, right? Two pool balls of equal mass. That means each of them have the same mass, so we can just plug in an M for our mass. Okay, and I'm going to show you kind of what happens here. V sub 1 is 3.1. V sub 2 initially was at rest. Okay, so we want to solve for V sub 1 prime and V sub 2 prime. However, it tells us our collision was perfectly elastic. Perfectly elastic. So we don't even have to do the math in this problem. Okay, what we're imagining here is pool ball A collides with pool ball B. Okay, A is moving at a speed of 3.1 meters per second. When this ball moves and collides here, there's a perfect 100% elastic collision that happens. And when we have a perfectly elastic collision, that means there's a 100% transfer of momentum between one object to the next. Okay? So what happens here is that pool ball A will come to a stop, and pool ball B will begin moving at 3.1 meters per second. Okay? When these two objects collide, there's going to be a perfectly elastic collision. So that means all of energy and all of the momentum from A was transferred to ball B. Ball A then takes its position at rest, and ball B ends up moving in that same direction with a velocity of 3.1 meters per second. Okay, we don't even have to do the math that goes into it. We don't even need the masses. Okay, the only time this works is when we have objects of equal mass. So that's why that was important to us. This does not have a perfectly, this relationship doesn't work perfectly every time unless our masses are equal to each other. Okay, because then essentially our masses cancel out. If our masses are not equal to each other, we don't have this perfect kind of switch of velocities here. Okay, so this works in situations where we have equal masses and it's a perfectly elastic collision. All right, our next problem here tells us a bat is swung with a velocity of 16.2 meters per second. The ball is moving in the opposite direction of the bat at 34 meters per second. The ball leaves with a speed of 42 meters per second. What's the final speed of the bat? Okay, so we have to be really mindful of our directions here. We have to actually visualize what's happening in this situation in a baseball game. Okay, we have a batter who's swinging the bat in the forward direction, right? We can consider that the forward direction. And we have a pitch coming in at us in the opposite direction. Okay, so let's go ahead and start writing down these variables here. We'll say that the bat is our first object. So mass of our first object is 22 kilograms. Velocity of our first object before our collision is 16.2 meters per second. Okay. The mass of our second object, which is the ball, is 0.94 kilograms. And the velocity of our second object before the collision, it tells us it's coming in at 34 meters per second, but it's opposite the direction of the bat, which means we need to have a negative included there. Okay, so our batter is swinging the bat in the forward direction. The pitch is coming in at the opposite direction, so that's why it gets a negative. Okay. The ball leaves the bat at a speed of 42 meters per second, so that means V sub 2 prime is equal to 42 meters per second. And it's going to be a positive 42 meters per second because it's not going to leave the bat the same direction that it was coming in at, hopefully, right? The batter doesn't foul it off. We're assuming they hit the ball toward the outfield. We assume that that ball is coming in the negative direction and it's heading out in the positive direction. Okay? And it asks us here to find the final speed of the bat, which means we're solving for V sub 1 prime. Okay? So if you want to go ahead and plug these things into your equation and try it to see if you can match my answer at the end, that's fine. Go ahead and pause and do that now. If not, I'm going to go ahead and work through the whole problem. Okay, so I'm going to use my elastic collision equation. Okay, mass of our first object's 22, velocity is 16.2, plus mass of our second object's 0.94, velocity is negative 34. Okay, then we're going to go back to our first object, which is our bat. We're solving for v sub 1 prime. We know v sub 2 prime is 42 meters per second. So now I'm going to go ahead and start plugging those numbers in, plugging the math in. Okay, so on my whole left side of my equation, I get 324.44 equals 22 v sub 1 prime plus 39.48. I still needed to subtract that 39.48 from the left side. And that leaves me really on the left side. I need to give myself some more room here. That leaves me with 284.96 equals 22 v sub 1 prime. Okay, so I'm going to take 284.96 divided by 22, and I get 12.95 meters per second. Okay, so our bat here is still moving in the forward direction, right? There was not enough momentum from the ball to make that bat rebound backwards, right? The momentum from the bat was enough to carry through, swing through that ball, make the ball change directions, but the bat still was following through. Okay, it was not enough momentum change to make the bat bounce backwards. Okay, so both of our final velocities end up being in the positive direction. All right, so we're going to move on to an inelastic collision now, which is when these two objects collide and they continue moving as one single motion, one single object. Okay, so here's an example here. We've got a train, a blue car, and a red car. So here our red car starts entering the picture, but before our collision, this is kind of the picture that we can have. Okay, our blue car starts at rest. Our red car has a velocity of 24 meters per second. Okay, so that's what our picture looks like before the collision. Okay. After our collision, we've got them joined together, right? They're joined as a one object, and they're going to continue moving in the rightward direction. Okay, after our collision, our masses are connected. So we use this equation underneath for an inelastic collision. Okay, so this equation right here is for inelastic collisions, things in which they stick together, they're combined after their collision. So after their collision, they end up as one object, so the masses of the objects are added together, and they've got one single velocity since we consider them to be one single object. All right, so let's go ahead and take a look here, and I'm going to give each of these cars a masses. I want a mass. I'm sorry, I want to ignore that. It said 10,000 kilograms. I want to ignore that. So this one says if the red train car has a mass of 30,000 kilograms, and the blue train car has a mass of 20,000 kilograms, what's the velocity of the cars after the collision? Okay, and when it asks for velocity of the cars, that means we're looking at the velocity of the object as one, right? The cars are now combined into one object. So let's go ahead and take a look at that. Okay, so M sub 1, which is our red train car, is 30,000. V sub 1 is 24 meters per second, and it was east, right? Our car was traveling to the right, which on a coordinate system is east. Our blue train car had a mass of 20,000 kilograms, and it was initially at rest. so we can plug in a 0 there. After the collision, we want to solve for these two objects. What's their velocity, right? We're looking at v prime, velocity of that single object after they've collided and stuck together. We're looking for the velocity of that singular object. So we're going to use our inelastic equation, which is m1 v1 plus m2 v2 equals m1 plus m2 times v prime. Okay, we've only got one final velocity, one velocity after collision, because there's only one object moving after collision. Okay, so let's go ahead and take a look here. Mass of the first was 30,000 times 24 plus 20,000 times 0 equals 30,000 plus 20,000 times v prime. All right, so 30,000 times 24 gives us 720,000. And this is plus 0, right? Our blue car had 0 momentum to begin with. And that gives us 50,000 times v prime. Okay, so we can drop that term there. We're going to take 720,000 divided by 50,000. We're going to get our v prime equal to 14.4 meters per second. Okay, since our velocity came out positive, that means it's moving east, right? It came out positive, so it's moving in the same general direction as our original red car was. Okay, it's just going to carry some of that momentum with it. Again, momentum was conserved throughout our entire collision, but it's got to move in the same direction as our momentum and as our velocity, so it's heading east. All right, for our last inelastic collision, if you would like to try this one by yourself, that's great. Go ahead and do that. You can hit pause, start working it by yourself, and then you can kind of fast forward to see if your answer matches here at the end or not. We're going to go ahead and work through this. I want you to first notice that our object is given in grams, okay? But before we do that, let's talk through what's happening here in our problem a little bit. 35-gram bullets fired at 200 meters per second. It hits and sticks to a target that sits stationary. The mass of the target's 45 kilograms. What's the velocity of the target after impact? So essentially, when this bullet hits its target, it might scoot the target just a little bit, right? It might move that target, keep it going just a little bit, but it's going to stick in it. So if you think about a block of wood or something that you're using for a target, your bullet fires and hits that target, and it might move with that bullet just a little bit. It's not going to bounce in the other direction. It's going to keep moving in the same direction as that bullet. Okay, hopefully we can visualize what's happening here. So let's go ahead and start our variables here. 35 grams is 0.035 kilograms. Velocity of our bullet is 200. Second object, which is our target, is 45. V sub 2 before our collision is 0 because it's initially at rest, sits stationary, initially at rest. Okay, V sub 1 prime. Sorry, we're not going to have V sub 1 prime. We're solving for V prime. Okay, because the velocity of the target after impact, it tells us it sticks to the target. So that's really target plus bullet. Okay, this is an inelastic collision, so it's the target plus the bullet. Okay, so let's go ahead and start plugging some numbers in here. 0.035 times 200 plus 45 times 0 equals 0.035 plus 45 times V prime. So I'm going to take 7 divided by that 45.035, and my V prime is equal to 0.155 meters per second. Okay, so when that bullet hits the target and starts to accelerate it, starts to move it forward in the same direction as the bullet, it's moving at a speed of 1.55 meters per second. Okay, so that's going to be where we stop today with collisions. You've got an equation for elastic collisions and inelastic collisions that you're going to put to good use. So both of those equations should be on your equation sheet and out handy for you to use during these problems. Remember that it is essential that you convert those grams. Anytime our mass is given in grams, must be put into kilograms. And you have to be very, very mindful about the direction of these objects, whether they're moving in the positive direction, negative direction, whether they're moving opposite of each other or in the same direction. Those negatives going into your velocity make a big difference. Okay, so you just have to be very, very careful if you've got something moving in the opposite direction and its velocity must be negative. Okay, so just be mindful of that as you're going through your problems here.